Okay, so today I'm teaching Kaylee, my friend, how to replace several vectors with a single resultant. So as you can see here, Kaylee, we have three vectors. This green box is an object with three forces being applied to it. So F1, F2, and F3 are those three forces. In these types of problems, you're going to have the magnitude and a way to find the x and y component of each vector. And so each of these three vectors you find in a different way, and that's why I like this problem, because you have to prove that there's three different ways to find it, to find x and y components of the vector. And so I guess try to visualize like a graph here. This is the y-axis and this is the x-axis. So like this, we'll start with F1. I guess I should explain. The goal here is to find the magnitude of our resulting force, the direction it's going, and the angle of that, the resulting force. And so in order to find any of them, in order to find this, we have to break all three of these down, like I said, into x and y components. So we'll start with the x component of F1. So the way to find the x and y components of F1, this little triangle helps us. Essentially, it's 500 newtons. So 500 newtons. Right, that's what this big line is equal to 5, as the x component is equal to 3. I'm sorry, -4, and the y component to 3. So envision a big triangle right here. It's the same. It's the ratio between those sides is the same as this little triangle. That's what I'm doing. And then through this equation, I can solve for x and y. So F1 as a vector is going to have the x and y component in it. That's what that means, just x component. It's I hat is what it's called. So when you take this ratio and then multiply it by -4, that's what you get. And then when you take this ratio and multiply it by 3, you're going to get 300 j hat, which is just the y component of it. And then when we write down F2 into its vector form, we're going to have to use trig, because it doesn't give us that small triangle, it gives us an angle, which is fine, we can do that. We're just going to take, so envision, I'm going to draw, that's our y, and our x-axis. This is our y and our x-axis, and this is F2. Imagine I moved this y-axis right here. That's the y, that's the x. See this triangle? So this is the y component of F2, and this is the x component of F2. This is my angle 60. So if I took the sine of 60, it would be the opposite over hypotenuse. So it's going to be the y component over the magnitude of F2, which is something we know. So if I solve for y here, I'm going to get the y component of F2 is going to be 350 times sine of 60. We can do that same thing for the x component, except it's going to have to be cosine of 60. Because cosine of 60 is the adjacent over hypotenuse. So when you solve for x and that, you're going to get the same thing except cosine. So those are the two harder ones. The easier one, by far, is F3. Since it lies on an axis, let me back up. So what this is saying right here is that this F1, right, is applying 400 newtons of force this way, directly this way, and 300 newtons of force directly that way. And that's why it's 500 at this angle. Same goes for that F2. F3 is exactly 400 newtons that way and 0 newtons up. And you can see that because it lies direct, it's straight, it's horizontal. Does that make sense?
Yep.
It's moving in the x direction 400 newtons and none in the y direction. That's why it's like that. And so the resultant force is just going to be all of these added up. All right, all the x's added up and all the y's added up. So when you add and so this tells us that it's going to pull that way 175 newtons and that way 600, about 600 newtons. It doesn't really tell us like how much it literally is pulling or which direction it is. That's what those two are going to tell us. And so, you ever seen that before?
Yeah.
If you solve for C, that's what you get, right?
Mm-hmm.
And so C is going to be our magnitude of the resultant force, right? Which is, this is our resultant force. This is the y component, and this is the x component of it. So a squared plus b squared is going to equal c squared. A and b are x and y components. This is our A. That's really rough, but does that make sense?
Yep.
That's where it's derived from, this equation. So when you do that, so that is the actual magnitude of this resultant force, right? That's literally exactly how much it's going to be pulling. And so theta, that one's a little bit trickier, in my opinion. But you gotta envision it again. That picture I'm gonna draw down here. The resultant force is right here. Here's my y component and my x component, which are two numbers that we know. They're right there. 175 and 603.109. This is our theta. that I'm looking for. Theta is just a Greek variable. It's a Greek letter, and we use it as a variable for angles. So what I wrote here is the tan of theta, opposite over adjacent, is 603.109 over 175. And so what we need to find is theta. We have one equation, one variable. So theta is going to be equal to tangent, the inverse tangent of 603.109 over 175. Just to clarify for the video, this is 175, 603.109, 627.99 newtons, and 73.8 degrees, counterclockwise from the x-axis. So that's how you find the resultant force, the magnitude and the direction it's going.